All right, so let me just. All right, now, hello and welcome to my talk about the Skyrmion Hall effect in Altermagnets. And because I know this conference is quite broad in terms of magnetism, let us digest the title together. So I will start in what skyrmions are. So I'm a theoretical physicist and I'm working in the field of micromagnetism. And what we basically do is you have a big magnet, your macroscopic sample, and you split it up into different small magnetic moments. And these magnetic moments can form textures. And one texture that we like, there's a whole slew of textures, as we have learned also from Sanjay. There are Hopfions and three-dimensional systems, but we're interested in skyrmions. And what's interesting about the skyrmions is that they have a topological protection, or what we call a topological protection. That means you cannot just deform this skyrmion here. In this case, we have a near skyrmion. You cannot just deform it into a ferromagnetic state, because by that you would introduce some kink into the magnetization field, and this would cost energy. So this topological protection makes skyrmions nice for us to just push them around. And what one important thing of this topological protection that basically describes everything is the so-called skyrmion winding number, or the topological charge of a skyrmion. This number is quantized to integers, and it can be positive or negative. And it is also responsible for a very nice effect that we can see with skyrmions, which is the Skyrmion Hall effect. So our driving force couples directly to this topological charge and creates a transverse motion. So when you have a skyrmion and apply an electric current to it into the x direction, you get a transverse component of your skyrmion trajectory. And this is not just some theoretical concept of ours. No, this actually has been measured, for example, in this measurement via MOOC microscopy. And we can see on the left-hand side, we have a skyrmion with charge -1. And we see that when applying current pulses into the x direction, the skyrmion trajectory goes into the positive y direction. So it has this transverse component in the positive y direction. And when we flip the charge of the skyrmion, the topological charge of the skyrmion, or the winding number, we inverse this Hall effect into the negative y direction. So this is also kind of a proof that that our current couples directly to the winding number. So let me go to the next topic. What is an altermagnet? So, ferromagnets, well, we have a net magnetic moment. All of our magnetic moments align. Our macroscopic sample has a net magnetic moment. And then we have antiferromagnets, where our magnetic moments anti-align, which means we do not have a net magnetic moment, and we do not break time reversal symmetry. A ferromagnet breaks time reversal symmetry. And then we have something like a ferrimagnet, where you have in both sublattices, where it is similar to an antiferromagnet, but you have in both sublattices different magnitude of your magnetic moments. And now the new cool guy kind of is an altermagnet, which in the first glance looks very similar to an antiferromagnet. But now the sublattices are not just connected by some translation, but they are connected by rotations. And there are multiple symmetries that an altermagnet can have. We are focusing on a D-wave altermagnet. This means it has a 90-degree rotation. But what is so nice about these altermagnets, that they are proposed to have, for one, the zero net magnetic moment of an antiferromagnet, but due to the time reversal symmetry breaking, they have nice dynamics similar to ferromagnets. So they kind of are proposed that in spintronics applications, those might be very nice to have. And how do we model an altermagnet? We model it by an anisotropic antiferromagnet. So in one sublattice, we have an exchange J1 into the x direction and exchange J2 into the y direction. And on the sublattice B, everything is flipped. And we have the interlayer exchange, which is antiferromagnetic. And we have other stuff that we need to stabilize skyrmions, like DMI and anisotropy. And what does this do to our skyrmions? Well, First of all, the anisotropic exchange gives us elongated skyrmions in both sublattices, and the 90-degree rotational symmetry of the Altermagnet gives us that in both sublattices, these skyrmions are rotated against each other. So now let me explain why there's a question mark in the title. So typically in compensated magnets, that mean magnets that have macroscopically a net magnetic moment, like the antiferromagnets or also our altermagnets, we would not expect the Skyrmion Hall effect because we do not have a net topological charge. That is because in one sublattice we have a skyrmion with charge 1, in the other sublattice we have a skyrmion with charge -1. So in the net sample they cancel each other, resulting in no topological charge, and therefore we predict that there should be no Skyrmion Hall effect. However, recent studies predict the Skyrmion Hall effect, and indeed, when you go to your favorite micromagnetic simulator, you will see when we implement this Altermagnet, we see that indeed we have a Skyrmion Hall effect. So this dot here is our skyrmion. This red dashed line is the y = 0 line, and we can clearly see at the end of the simulation we have a transverse component, and the current here is only applied into the x direction. So what's going on there? Theoretically, we would predict we don't have a Skyrmion Hall effect, but simulations show we have one. So what's going on there? For that, we need to understand how the dynamics of magnetic moments are described. And they are described by the Landau-Lifshitz-Gilbert equation, where we have this precision term around the effective magnetic field, which also includes our interaction or external magnetic fields. Then we have our damping term of our precession. And we have additional torque terms. And typically we model an electric current by Changli spin transfer torque, which is given by where the torque is given by those derivatives into the direction of the current. And well, this equation is not solvable analytically in most cases, so we need to solve it numerically, and therefore we need to discretize everything, meaning also including we need to discretize the derivatives. And this discretization is what gives us a problem in altermagnetic systems. Because you see the error that we do in the discretization, that depends on the elongation of the skyrmion into the direction of the current. And because the skyrmions are elongated and rotated in the two sublattices against each other, this discretization error is different in both sublattices. So, and typically in compensated magnet, the Skyrmion Hall effect in one sublattice would completely cancel out the Skyrmion Hall effect in the other sublattice. But now when we have an anisotropic error, we do not see this canceling effect because they are not the same. The error in both sublattices is not the same. So this is why we propose that the altermagnetic Skyrmion Hall effect that we will see with a standard spin transfer torque is just a discretization artifact. And to kind of prove this point, typically the derivatives are discretized with a symmetric finite difference, where the first order is of the first error is of order a squared, like discretization to the power of 2, and then we of course have higher errors. So to prove our point that this is just a discretization error, we have basically two options. We can implement the discretization not in a 3-point stencil, but in a 5-point stencil, and this means we get rid of this order 2 error here. Or we could implement this order 2 error in our analytical description, which in the Thiele equation would refer to a higher gyro tensor or dissipation tensor, and some would do like our error would be physical and see if we now match what our simulations give us. And this is exactly what we did. So we calculated the steady state velocity for different simulation cells for a standard Changli spin transfer torque. And first of all, we see, well, the Hall angle is heavily depending on our discretization, which is kind of always a bad sign and could hint that we have a large influence of a numerical error. And then when we do the analytics with a higher gyro and dissipation tensor, meaning we calculate our Skyrmion Hall effect with that error in mind, we see that the analytics match very well our simulations. And now if we implement the 5-point stencil into Mimax, or into our simulation program, we see that with a order 4 implementation, the Skyrmion Hall angle is is much lower than with the order 2 implementation. And this basically all proves that the Skyrmion Hall effect is just a discretization error. That the Skyrmion Hall effect that we see in an Altermagnet is just a discretization error. So is now all hope lost? And we claim no. We just have to be a bit more careful, think a bit harder, and dig a bit deeper to find the Skyrmion Hall effect in an Altermagnet. Because maybe we need to rethink the way how spin transfer torque works in an Altermagnet. So typically, you apply a spin transfer torque in both sublattices, which a spin transfer torque of the same magnitude in both sublattices. And this is fine for antiferromagnets or for ferromagnets. But in an Altermagnet, we have a different dispersion due to the time reversal symmetry breaking and the anisotropic exchange. So the sublattices are distinct and should carry different current densities. And if they carry different current densities, then by design, the Hall effects would not cancel each other in the two sublattices, and we would see a Skyrmion Hall effect. And this is exactly what we did. We did simulations and also the analytics via the Taylor equation, and we see for 0 difference between the current densities, we don't see a Hall effect like predicted. But when we increase the difference between the magnitude of velocities, we see that we get a Hall effect. And now I will come to my conclusion. First of all, we predict that there is no analytical Skyrmion Hall effect expected in an Altermagnet. What we see in simulations is due to an anisotropic discretization error in both sublattices. And this kind of gives the take-home message of this talk that when simulating an Altermagnet, you have to be careful because the discretization error can be different in both sublattices. But in real systems, we predict that there might still be a Skyrmion Hall effect due to the different dispersion in the in each sublattice. And in the end, I want to thank you for your attention. I want to thank my supervisor, Jan, for his help during this project. And I want you to stay tuned for our preprint that is coming up soon. Thank you for your attention.
Okay, thank you very much, Nicholai. Is anyone has any question in the chat? Okay. I was wondering because these kind of materials are like an antiferromagnetic ordinal, right? So in principle, if you conduct them to move very fast, like relativistic velocities, they have this kind of contraction in the direction of movement, but expansion in the transversal direction, right? So given that you have this kind of 90 degrees rotated skyrmions in each lattices, I was wondering if once you trigger the dynamics, you will see something unexpected with respect to any kind of compensated antiferromagnets of A-type.
In that sense, I think they would behave fairly similar to an antiferromagnet. So I would.
Okay, yeah, but I mean the width along each direction in each lattice is different, right? So along
Yes.
one direction, one lattice is the shorter one. So it will move in the same direction given that it is transverse deflection, or
I don't know. I have not thought about this yet. I would need to think about this a bit more to give you
Sure.
a satisfying answer. Sorry.
There is a question in the chat from Rakul Flag. Can you explain why you expect different current densities in different sublattices?
So yes, this is basically because due to the different exchange along the current direction in both the sublattices, the overlap between the orbital atoms on the lattice sides is different, and therefore it is easier. Like you basically expect the higher hopping amplitude or a different hopping amplitude along the current direction in both sublattices, and therefore you would expect a higher current density.
Okay, thank you very much, Nicholai. Thank you for your presentation.